Right now, there is an ocean on another world. Not a theory, not a model, not a hopeful extrapolation from a handful of ambiguous measurements. An ocean, liquid water, confirmed by multiple independent instruments on multiple independent spacecraft across 4 decades of data from a moon that, from the outside, looks like nothing more than a cracked ball of ice drifting in the shadow of Jupiter. Most people have heard of Europa. Most people know the general outline. Ice shell, maybe water underneath, possibly interesting. And what most people have not heard is what the data actually says. Not what scientists hope is there, not what the models predict might be there, and what the instruments have directly measured, what they have confirmed beyond reasonable scientific dispute. And what Europa Clipper, the most capable planetary science spacecraft NASA has ever launched to the outer solar system, is measuring right now as it begins its closest passes over a surface that has been waiting 4.5 billion years for someone to look at it properly. Stay with me. Because by the time this is over, the word habitable will mean something different to you than it did when you started watching. Here is where the story actually begins. Not with Europa, with a decision made in 1979 by a group of scientists looking at photographs taken by a spacecraft that was never supposed to be there in the first place. Voyager 1 was built to photograph Jupiter and Saturn and then go quiet. It was not designed as an ocean hunting mission. It was not pointed at Europa with any particular expectation of what it would find. But when it flew past Jupiter in March of 1979 and sent back the first close-up images of the planet's 4 largest moons, something in those images stopped the team cold. Europa's surface was wrong. Not wrong in the way that a failed instrument produces wrong data, wrong in the way that a thing looks when it does not match any framework you have ever used to understand it. Every other moon in the solar system that scientists had seen up close by that point was covered in craters. Craters are the default surface condition of any world old enough to have been sitting in the solar system for billions of years. Rocks hit things. Craters accumulate. The older the surface, the more craters. That is not an opinion. It is a physical fact verified across every solid body humanity had ever examined. Europa had almost none. Its surface, photographed for the first time in 1979, was one of the smoothest in the entire solar system. Smoother than Earth's ocean floor, smoother than anything that had any business being that smooth after 4.5 billion years of sitting inside the most crowded gravitational neighborhood in the outer solar system. Jupiter's radiation belts, Jupiter's tidal forces, the constant bombardment of debris that fills the space around the largest planet ever to form in our solar system, and stretched across that impossibly smooth surface was a network of reddish-brown lines, cracks, thousands of them, running in every direction, crossing each other, layering over each other, some extending for thousands of miles across the surface in long, graceful arcs that had no obvious geological explanation, not volcanic, not tectonic in any way that matched anything seen on a rocky planet. Something else entirely. Something that, when the scientists at JPL looked at those images long enough, it started to look uncomfortably familiar. It looked like sea ice, the kind of fractured, refrozen ice that forms on the surface of Earth's polar oceans when the water underneath it shifts and the ice above it cracks and separates and refreezes into new patterns. The kind of surface you get not from a dead frozen world, but from a world with something liquid moving underneath it. The implication was immediate and it was enormous. And in 1979, with exactly one set of flyby photographs and no other data, it was also completely unproven. So the question sat for 17 years it sat. Then Galileo arrived. The Galileo spacecraft entered Jupiter orbit in December 1995 and spent the next 8 years making repeated close passes over Europa, returning data that transformed the 1,979 photographs from a suggestive anomaly into something that could no longer be explained away. The first confirmation came from the magnetometer. Jupiter's magnetic field is the largest structure in the solar system, a vast, rotating envelope of charged particles that extends hundreds of millions of miles in every direction from the planet. Every moon inside that field is immersed in it. And if you move a conductor through a magnetic field, you generate a secondary magnetic field of your own. This is basic physics. It is how generators work. It is how transformers work. It is one of the most reliably tested principles in all of science. When Galileo measured Europa's magnetic environment during its close passes, it found exactly this: a secondary induced magnetic field, a signal that could only be produced if something inside Europa was conducting electricity, something liquid, something that extended across the Moon in a layer large enough to generate a detectable signal in Jupiter's rotating field on every single pass Galileo made, regardless of the geometry. The only substance that fits the conductivity, the geometry, and the induction pattern is saltwater. Not ice, not rock, not any exotic solid compound, a global subsurface ocean of liquid saltwater. That is what the Galileo magnetometer data says, not suggests, says the ocean is not a hypothesis the data is consistent with. It is the conclusion the data requires. Here is the scale of what that means, and why scientists who have spent careers studying it still describe the moment they understood it as one that shifted something permanent in how they think about the universe. Europa is roughly the size of Earth's moon. It sits 485 million miles from the Sun. At that distance, the surface temperature averages around minus 260 degrees Fahrenheit. Nothing on its surface is liquid, nothing on its surface could be liquid. The ice shell covering Europa is estimated to be somewhere between 10 and 30 miles thick, frozen hard by temperatures that would make the coldest place on Earth feel warm by comparison. And underneath that frozen shell, underneath miles of ice that has been sitting at temperatures incompatible with liquid water for as long as the solar system has existed, there is an ocean estimated to contain more liquid water than every ocean, every sea, every lake, every river, and every underground aquifer on Earth combined. Twice as much water. A global ocean with a depth estimated at somewhere between 60 and 100 miles, sitting in total darkness under enormous pressure, completely sealed from the sky above it by a shell of ice that has never once cracked all the way through, and it has been there liquid for an estimated 4 billion years, not because Europa is warm, not because it sits close to any heat source in the conventional sense, because of Jupiter. The gravitational relationship between Europa and Jupiter, and between Europa and the other large Galilean moons, creates a process called tidal flexing. As Europa orbits Jupiter, the planet's immense gravity pulls at it unevenly, stretching and compressing the moon's interior in a continuous cycle that generates heat through friction, in the same way that bending a metal rod back and forth generates heat at the bend point. That tidal heating is what keeps the ocean liquid, not sunlight, not radioactive decay alone. The gravitational interaction with the largest planet in the solar system, an interaction that has been running continuously for 4 billion years, pumping heat into Europa's interior at a rate sufficient to maintain a global ocean of liquid water beneath a shell of ice in a place where liquid water has no business existing at all. This is the first thing the data confirmed. The ocean is real. The ocean is liquid. The ocean has been liquid for a very long time. And here is where the story stops being about physics and starts being about something else entirely. The question is not whether the ocean exists. That question has been answered. The question is what is in it. To understand why that question matters in the way that it does, you need to understand what life actually requires, not what life prefers, not what life thrives in, what life, at its most fundamental level, requires in order to exist at all. The scientific consensus on this has evolved significantly in the last 40 years, specifically because of discoveries made not in space, but in the deepest parts of Earth's own oceans. In 1977, the same year Voyager 1 launched, oceanographers using a deep-sea submersible called Alvin discovered something at the bottom of the Pacific Ocean that fundamentally changed biology. Hydrothermal vents, cracks in the ocean floor, where superheated water laced with minerals and chemicals poured out from the interior of the Earth into the freezing, crushing darkness of the deep ocean. No sunlight reached there. No photosynthesis was possible. Every prior assumption about the energy source required for life was inapplicable, and surrounding those vents, in water hot enough to be toxic, in darkness complete enough to be absolute, in pressure sufficient to crush a submarine, was life. Tube worms 6 feet long, shrimp with no eyes, bacteria living in temperatures above the boiling point of water at sea level, metabolizing sulfur compounds and chemical energy directly from the vents, an entire ecosystem, complex and self-sustaining, existing in conditions that every prior model of habitability said were incompatible with life. That discovery rewrote the definition of habitable, not by expanding it slightly at the edges, by eliminating sunlight as a requirement entirely. Life, it turned out, does not need a star. It needs liquid water, a chemical energy source, and enough time. Europa has all three. The tidal flexing that keeps the ocean liquid almost certainly also drives geological activity at the ocean floor, cracks in the seafloor, hydrothermal systems, the same kind of chemistry that powers the ecosystems around Earth's deep sea vents, the same liquid water, and 4 billion years of time. If the conditions that produce life at the bottom of Earth's oceans exist anywhere else in the solar system, Europa's seafloor is the most likely place. That is not speculation. That is the direct application of the only data set have about where life forms in conditions without sunlight applied to the only other place in the solar system where those same conditions are confirmed to exist. This is why Europa sits at the center of astrobiology in a way that Mars, for all its surface features and ancient riverbeds, does not. Mars may once have had liquid water, Europa has it now. Mars may once have had conditions suitable for life, and Europa has them now. The question is not historical in Europa, it is present tense. But here is the limitation that has defined everything about this story since Galileo's magnetometer first confirmed the ocean in the late 1990s. We cannot see it. The ocean is sealed. The ice shell above it is miles thick. No signal we can send from a spacecraft in orbit penetrates that ice cleanly enough to directly image the water below. Every measurement that has been made of Europa's ocean has been made indirectly, inferred from surface features. Magnetic signatures, gravity measurements, thermal readings, spectroscopic analysis of the surface chemistry, and the ocean has been confirmed by instruments that never touched it, never saw it, never sent a single photon through the ice and received one back. It has been confirmed the way a doctor confirms a heartbeat through a stethoscope pressed against the chest. You hear it, you measure it, you cannot see it directly, and everything we do not know about that ocean, including how deep it is, how salty it is, what chemistry is happening at its floor, whether that chemistry is biologically active in any sense, whether anything in that water has crossed the threshold from complex chemistry into biology, requires either a mission that can penetrate the ice or instruments capable of reading the ocean's influence on the surface. Above it, in ways that no mission before Europa Clipper was designed to do, Europa Clipper launched on October 14, 2024, and it is currently in transit. It'll reach Jupiter orbit in April 2030, and when it arrives, it will carry 9 science instruments specifically designed to do what Galileo could only partially attempt, not a flyby, not a brief pass through the Jupiter system. A dedicated multi-year orbital mission around Jupiter with 49 close flybys of Europa specifically designed to build the most complete picture of this moon's ocean, its ice shell, its surface chemistry, and its potential habitability that any instrument ever constructed has ever been positioned to produce. The spacecraft is the largest planetary science mission NASA has ever flown to the outer solar system. Its solar panels span more than 100 feet. Its instruments include a radar system designed to penetrate the ice shell and map the ocean beneath it, a magnetometer capable of measuring the induced field with 50 times the sensitivity of Galileo's instrument, a mass spectrometer capable of analyzing individual molecules in Europa's thin atmosphere and in any material ejected from the surface, a thermal imager capable of detecting temperature anomalies on the surface as small as a fraction of a degree, and a suite of cameras capable of imaging the surface at resolutions fine enough to see features the size of a parking space. This is not an incremental upgrade over what came before. It is a different category of instrument entirely, pointed at a target whose basic existence the data has already confirmed, designed to answer the questions that confirmation left open. The radar instrument alone is worth understanding in detail because it represents the closest thing humanity has ever built to a direct look at Europa's ocean. The instrument is called REASON, which stands for Radar for Europa Assessment and Sounding, Ocean to Near Surface. It operates on 2 frequencies simultaneously, one designed to penetrate deep ice and one designed to map the structure of the upper ice shell. As Europa Clipper makes each of its 49 close passes, REASON will send radar pulses downward through the ice and measure the reflections that come back. Ice and water reflect radar differently. The boundary between ice and liquid water is detectable. If the ice shell is thin enough in any region, or if pockets of liquid water exist within the shell itself closer to the surface, REASON will find them. If there are regions where the ocean has come close enough to the surface to create detectable interfaces, those interfaces will show up in the data. This is not guaranteed. The ice may be thick enough and uniform enough to prevent a clean detection of the ocean below, but it is the most direct attempt ever made to actually read the structure of the barrier between the surface of Europa and the water beneath it, and it is flying right now in transit, carrying that instrument toward a target it will reach in 2030, but Europa Clipper has already done something significant before it reached Europa. During its journey to Jupiter, the spacecraft performed a flyby of Earth in December 2024 and a flyby of Mars in March 2025. Using each planet's gravity to accelerate toward the outer solar system, during the Earth flyby, It tested and calibrated all 9 of its science instruments in real conditions. Every instrument confirmed functional, every instrument producing data consistent with design specifications. The team at JPL used the Earth flyby to do something else as well. They pointed Europa Clipper's instruments at Earth itself and ran a blind test. They asked if this spacecraft were approaching Earth for the first time, with no prior knowledge of what was here, would its instruments detect the signatures of an inhabited world, the ocean surface, the atmospheric chemistry, the thermal signature of biological activity at a planetary scale? The answer was yes, not conclusively, not in a way that would have allowed a scientist to declare with certainty that life existed on Earth, without already knowing the answer, but the chemical and physical signatures that biology produces at a planetary scale were detectable. The instruments were sensitive enough to find them. This is not a trivial test. It is the same test those instruments will apply to Europa. If there is biology happening at Europa's ocean floor at anything close to the scale of Earth's deep-sea vent ecosystems, if the chemistry of that biology is reaching the surface of the ice in any detectable form, the instruments on Europa Clipper are, for the first time in the history of this mission, potentially sensitive enough to find it. Potentially, the word is important. Europa Clipper is not a life detection mission in the strict scientific definition of that term. It is a habitability assessment mission. The distinction matters. A life detection mission is designed to conclusively confirm or rule out the presence of biology. Europa Clipper is designed to determine whether the conditions for life exist and to constrain how favorable those conditions are. The difference is important because directly detecting life in Europa's ocean from a spacecraft in orbit is, with current technology, almost certainly impossible. The ocean is too deep, the ice is too thick, the signals that biology produces are too faint to survive the passage through miles of ice and the distance to a spacecraft above. What Europa Clipper can do is read the surface for signs that the ocean below is chemically active in ways that are consistent with the processes that support life, and determine whether any material from the ocean has reached the surface in a form the instruments can analyze. This is where Europa's plumes become one of the most scientifically significant questions of the entire mission. In 2012, the Hubble Space Telescope detected what appeared to be a plume of water vapor erupting from Europa's southern polar region, a jet of material shooting up from the surface into space, similar to the geysers Voyager 2 had confirmed on Neptune's moon, Triton, and similar mechanism to the plumes that Cassini had directly flown through at Saturn's moon, Enceladus. The detection was tentative. The data was not conclusive, but subsequent Hubble observations in 2016 confirmed a plume-like feature in roughly the same location at a similar altitude, with similar characteristics. And data reanalyzed from Galileo's 1997 close flyby of Europa showed magnetic and plasma signatures consistent with the spacecraft having flown directly through a plume without knowing it at the time. A detection that was only recognized after the Hubble observations gave scientists something specific to look for in the old data. The plumes, if they are real, and the data increasingly suggests they are, would represent something extraordinary. Material from Europa's ocean, or at minimum, from liquid water within the ice shell itself, being ejected directly into space. No drilling required, no penetration of the ice. The ocean, or something connected to it, bringing itself to the surface and launching samples into space where an orbiting spacecraft can fly through them and analyze them directly. Enceladus has already proven this is possible. Cassini flew through Enceladus plumes multiple times and found water ice, salt, silica particles, organic molecules, molecular hydrogen, and carbon dioxide. Every single one of those detections added to the case for a habitable ocean beneath. Enceladus's ice, it can measure the ratio of different chemical compounds in a way that distinguishes between chemistry driven by geology and chemistry that has been influenced by biology. It cannot confirm life, but it can find the chemical fingerprints that biology leaves behind, and it can do so in real time, in direct samples of material that originated below Europa's ice shell during flybys that will bring the spacecraft within 16 miles of the surface. Europa's plumes, if they are similarly accessible, offer the same possibility for a world whose ocean is estimated to be significantly larger, significantly older, and potentially significantly more chemically complex than Enceladus. Europa Clipper's mass spectrometer is designed specifically to analyze plume material if the spacecraft passes through any during its 49 close flybys. The instrument can detect individual organic molecules. It can identify amino acid precursors, 16 miles, For context, the International Space Station orbits Earth at roughly 250 miles. Europa Clipper will pass Europa at less than a tenth of that distance, close enough for its cameras to image the surface in extraordinary detail, close enough for its mass spectrometer to sample the thin atmosphere directly, close enough for its radar to make its deepest possible penetrations of the ice, and close enough to have a real possibility of flying through any plume material that is active during the pass. The first of the science flybys is currently scheduled for 2031. The 49 total flybys are planned to be completed by around 2034. By the time the mission is complete, scientists will have more data about Europa than all previous missions combined, multiplied by an order of magnitude. Here is what that data will and will not be able to tell us. It will tell us the thickness and structure of the ice shell across most of Europa's surface. It will tell us whether pockets of liquid water exist within the ice itself, closer to the surface, potentially accessible to future missions. It will tell us the salinity and basic chemistry of the ocean with far higher confidence than current estimates allow. It will tell us whether the seafloor is geologically active in a way consistent with hydrothermal systems. It will tell us whether organic molecules are present in material reaching the surface. It will tell us whether the conditions are not just theoretically compatible with life, but actively supportive of it in the specific ways that matter for biology. What it will not tell us is whether anything is alive in that ocean right now. That question, the one that makes this story matter at the deepest level, cannot be answered from orbit. It requires getting below the ice, and getting below the ice on Europa is one of the most technically demanding challenges. In a history of planetary exploration, a Europa lander would need to survive the radiation environment near Jupiter, which is the most intense natural radiation field in the solar system outside the Sun itself, and is capable of destroying unshielded electronics within hours. It would need to drill or melt through somewhere between 10 and 30 miles of ice, maintaining a powered, functioning system throughout a process that could take years. It would need to then operate in an ocean at crushing pressure, in complete darkness, while transmitting data back through the ice it had just penetrated, up through the surface, across 485 million miles of space, through a communication delay of up to 45 minutes each way to engineers who would have no direct control over any real-time decisions the system needed to make. No such mission is currently funded. That is the span of this story, 1979 to 2024. One image taken by a spacecraft that was never supposed to find it, to a mission that took 4 decades to plan, fund, build, and launch, designed specifically to follow the question that image first raised. The ocean has been there the entire time. We have been looking at it from the outside, inferring its existence from magnetic fields and surface geology, and the behavior of a moon that has been telling us something is moving beneath its skin since the first time we looked at it closely. Europa Clipper is the closest we have ever come to looking directly. The first science flybys begin in 2031. The full dataset will be complete by 2034. And somewhere in that data, in the radar returns and the magnetometer readings and the mass spectrometer samples and the thermal images of a frozen surface above an ocean that has never seen light, will be the clearest answer humanity has ever obtained to the question that has defined astrobiology since the first hydrothermal vent was photographed at the bottom of Earth's ocean in 1977. Is the water there enough? Or is there something in it? The ocean is real, it is deep, it is old, it is dark. And right now a spacecraft is on its way to find out what is inside it. If you want to follow every confirmed finding from Europa Clipper as it arrives, every radar return, every mass spectrometer reading, every close flyby result reported at the weight the science actually deserves, rather than buried in a headline and forgotten. Subscribe now and turn on notifications. This channel covers what the instruments actually measure, what they confirm, what they leave open, and what it means for the only question in planetary science that has ever really mattered. The signal from Europa Clipper is already traveling. The ocean has been waiting 4.5 billion years. We are finally almost close enough to hear what it has to say.